So now is our practice time. Before we start our reality practicing, let's have a closer look to our model. And this is our model. Our upper rotating shaft stick out of the shaft, and the other end was tied with a thread to make it stable. In the upper pendulum, we use 2 popsicle sticks to compose it, and we clip it together to make it fall apart because the popsicle stick cracked a bit when I drill a hole. And the plastic thread is to make the popsicle stick stay where they are. The black eraser in the front and in the back is the M1 in the double pendulum model, and this chopstick made up the lower rotating shaft. This is the lower pendulum, and the white eraser is the M2 in the double pendulum. Why we designed the upper pendulum to be 2 popsicle sticks? Because we have to make sure that the lower pendulum can rotate smoothly without hitting the upper pendulum. Okay, so now let's show our modeling. And now let's review the animation we see in the third video. Okay, you can see the biggest difference from the animation and the reality modeling is that the animation just keeps on going, but the modeling stops after 5 to 10 seconds time period. It's because the friction in the reality model is too big to make it stop, or the lower pendulum hits something on the upper pendulum and slow it down. Yeah, but from the two, like animation and the real-time modeling, we can conclude that the double pendulum is truly chaotic, because you can see in the reality modeling that I start the model in like similar position, but the motion every time is different. And in the animation, in the real-time modeling, there's no 2 tracks with the same trace. So we can conclude that the system of double pendulum has rich dynamic behavior and strong sensitivity to initial condition. And the strong sensitivity to initial condition, we can see that very clearly from our real-time modeling. Okay, so this will be our topic, and thank you for your listening.